Hello friends, in this video we are going to discuss about general solution of equation of vibrating string fixed at both the ends. So this is the equation, differential equation to represent this motion. Now let me start. Okay, the differential equation of vibrating string is given by second order derivative, partial derivative with respect to time t of y. Y represents the displacement at position x with in time t. Okay, y represents the displacement at position x at a point at displacement of a point on the string at position x in time t. Okay, that is what it does represent. Okay, c square, again second order derivative of y with respect to position. Okay, so here is the string, suppose, and this, let me take this one as x is equal to 0 and this is x is equal to L, so that the length of this string is L. Okay, now you see, so suppose this is a point at x is equal to, suppose x, right? Now its displacement will vary with time. Again, at the same time, the point at different position, this is suppose at x1, this is suppose at x2, this point is at x2, so its displacement may not be same as this point at the time t, right? So similarly the displacement of this point at time t1 and t2 may be different, right? So that's why you see we have seen that this capital Y depends on t as well as x. So we can write this as a product of two functions. So we can write this one capital Y as small y of x and small y of t. We can write that way. So we will discuss this later again. This is equation number 1, where c is equal to, the c is the velocity of transverse wave along the string, right? And we can write capital Y is equal to small y of t into small y of x. Let me write that way, and this is suppose equation number 2, right? And you have already got in senior secondary level that simple harmonic function that can be written as, linear combination of sine and cosine function. That's why let me write small y omega t is equal to a plus b sine omega t. As we are dealing with simple harmonic motion, a and b are arbitrary constants here. This is suppose equation number 3. Omega is the angular frequency, which is equal to 2 pi nu is the frequency here, nu is frequency, right? Now let me differentiate equation number 2, differentiating both sides of equation number 2 with respect to time t twice. Okay, we're going to differentiate it twice. So here we are going to differentiate it partially, so with respect to time, that's why we're going to consider this function of x as constant, because we are going to differentiate with respect to t partially. So, and as we are going to differentiate it twice, so we're going to write second order derivative with respect to t of capital Y. That's going to be equal to small y of x is taken as constant, then second order derivative of small y, which is a function of t with respect to time t, right? That's what we're gonna have. So hope you have understood this. Now you see small y of x, this y of t is this one. So let us differentiate it twice. Okay, so then what we're gonna have, you see. Okay, now let me take a new slide. So first let me copy the equation number 3. Here is the equation number 3, and what we need to find, let me obtain this part, okay, this stuff. So let me differentiate it twice. If you differentiate it once partially, then what you're gonna have with respect to time t, if you differentiate it, it's gonna be minus a omega sine omega t, as it is a function of function. Again, you have to differentiate omega t, so that's why this omega comes out, right? Plus b omega cos omega t. Then again, as we are going to find the second order derivative of y, so again, if we differentiate this y of t with respect to t, then derivative of this, again it will be cos omega cos, so a omega square cos omega t, then this is cos, that's going to be sine, so minus sine b, now it becomes minus b omega square sine omega t, right? You can take minus omega square common, so within bracket you're going to have a cos omega t plus b sine omega t. Now let me copy this result. Okay, now here you see, so that's why instead of this, now we can write this result. Here you see, we can write this result. So hope you have understood this, right? So now let me copy this system and let me go to the next slide. Here you see, okay, this was the last step we have got. Now let me clean these things. Okay, now you see this part can be replaced by y of t. Okay, so that's why what we're gonna do, let me cut it and let me go here. Okay, so that's why we can write minus is taken outside, omega square is there, omega square y of t. That's what we can write using equation number 3. Okay, so from equation number 3 we can write this as y of t, small y of t, right? That's what we have got. Now from equation number 1, what you can write, okay, this part from equation number 1, let me go back to previous slide. Here you see, this is equal to this, right? Let me copy this equation number 1. Here you see, so this is the equation number 1, so we can replace this term by this one, right? If we do that, then what we're gonna have, just wait, so we can write here c square second order derivative of y, capital Y, with respect to x, right? That's what we can write. Now let me cut it, just wait. Okay, now again here you see this c square second order derivative of this capital Y. This capital Y is nothing but product of small y of x and small y of t. We can write that way. Okay, so minus omega squared small y of x small y of t. So here what we have used using equation number, so we have used this equation number 2, right? So instead of this capital Y, we have put this value, right? Hope you have understood this equation number 2, right? So now here you see c square, we're gonna take this as constant now because we are differentiating with respect to x, so we're gonna take the function of x only. So y of t is small y of t is taken as constant. Second order derivative of y of x with respect to x, right, is equal to minus omega square y of small y of x into small y of t. So here these two cancels, and this implies second order derivative of y of x with respect to x minus omega square by c square small y of x. That's what we have got, right? So this is suppose equation number 4. Let it be equation number 4. Okay, now let me take a new slide. Okay, so let me copy this equation number 4 and let me go to new slide. Now you see this equation can be written in this form. Let me show you. It can be written in this form, right? Just let me write this way. Okay, and the solution of the general solution of this kind of differential equation is of this form. Let me show you. Y of x is equal to a1 cos, so whatever it is, the constant, cos omega by c x plus b1 sine omega by c x. Okay, so why and how, that's not our concern here. You must remember this solution. Suppose you have a square here, then you have to put a here. Okay, that's how you have to remember that thing. Okay, so that's why let me cut it. So general solution of equation number 4 is given by small y of x, that's equal to a1 cos omega by c x plus b1 sine omega by c into x. Okay, let it be equation number 5. Let it be equation number 5. Now you see from equation number 2, this one, you see from this equation, let me copy this equation. From this equation number 2, what we can write, so from equation number 2, this y of x can be written here, and y of t we have already considered that a cos omega t plus b sin omega t. We can put those, right? So then what we're gonna have, that a cos omega t, this one we are putting this y of t, where is that, this one, so we are putting this one here, and also this value y of small x as well. Okay, b sin omega t into, then instead of y of x we're going to put this is y of x, this is small y of t, this is small y of x. That's it, right? Hope you have understood this. Now you see, let it be equation number 6. Let it be equation number 6. Now the wire is fixed at both ends, x is equal to 0 at x is equal to L. At these 2 points displacement must be 0, right? Because these 2 points are fixed for all values of t, right? So condition 1 at x is equal to 0, this capital Y is equal to 0 for all values of t, right? Okay, if that is the case, then you see capital Y is equal to small y of t into small y of x. So here this at this point this capital Y is equal to 0, so that's why we can write this product of these two is equal to 0. If that is equal to 0, then we can write that this thing is equal to 0, right? Okay, so instead of these two we can put this two, right? Hope you have understood this. Or you can say simply like this, that this capital Y is replaced by this result, right? So that then this equation number 6 becomes for this condition that let me copy this instead of writing each and every time again and again. Okay, we can write this is equal to 0, right? This is equal to 0. So where it is 0, at x is equal to 0, so we can replace this x by 0, right? So if we replace this x by 0, then here we're gonna get cos 0 and here we're gonna get sine 0. Okay, now you see cos 0 is 1, sine 0 is 0, so that's why we have here a1 is equal to 0, because only we have got a1 into 1, this part becomes 0 on putting x is equal to 0, right? That's why we have got this. So this implies that a1 is equal to 0. If this a1 is equal to 0, then this equation will be, so here this term will be equal to 0, right? Then this equation number 6 becomes, on putting a1 is equal to 0 here, then equation number, let me take a new slide. Therefore equation number 6 implies, so what is 6? Let me copy this 6, equation number 6. This is equation number 6, and on putting a1 is equal to 0, so it becomes of this form. Just wait. So that's what we're gonna have, right? Now let it be equation number, so what was the last equation? Equation number 6. So let it be equation number 7. Okay, let it be equation number 7. Now you see there is one more condition number 2, that at x is equal to L, also capital Y is equal to 0, because this string is fixed at x is equal to 0 as well as x is equal to L. So that's why these 2 points cannot vibrate, right? So hope you have understood this. So for all values of t, if that is the case, then this equation number 7 implies, let me copy this part, okay, and let me write here. So here you see, now let's put x is equal to 0 here, sine 0 is going to be 0, right? Sorry, not 0. Here we are going to put x is equal to L, because we are considering this condition, x is equal to L, so here we're going to put L, right? That's equal to 0 because y is equal to 0 here. So instead of y, we're going to put 0, right? So this implies that b1 sine omega c into L is equal to 0, and we know that general solution of sine theta is equal to 0, the general solution of sine x is equal to 0 is sine of n pi, where n is equal to 0, 1, 2, so on, dot dot dot. So here we're going to write sine n pi, n is equal to 0 1 2 3 dot dot dot, right? So let's put this one here, here, here. Okay, let me replace this omega. Okay, so then what you're gonna get then by L, and here you see, just wait. Now let me write this part. Okay, then an cos n pi c by L into t bn, sorry, there supposed to be plus sign, bn sine n pi c by L, right? So this is the required solution that we needed to obtain. So let me use here capital A and capital B n. Okay, so let me use here capital B, and these are arbitrary constant. So I have used here capital because so that you will not be confused with this small bn. Okay, so that is the solution of this equation of vibrating string fixed at two ends. And if you put n is equal to 1, n is equal to 2, then you will get first mode of vibration of string, then you're gonna get the second mode of vibration of the string, and so on, right? So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.